Uh, in this session, we are going to talk about this general idea of reformulations because the next set of lectures are going to focus on how to make these default algorithms faster and easier to solve. Uh, so we have seen 3 or 4 different algorithms. One is nonlinear branch and bound, Bender's decomposition, uh, outer approximation, and LO and LO. Uh, and all of these algorithms very broadly assumed that the functions are convex and differentiable and nothing beyond that. Okay, so practical problems can be solved using simple implementations of these algorithms, but as their size increases, the running time increases exponentially. And one way to tackle that growth is to look at the structure of the problems and try to do some very nice transformations or exploiting some parts of the problem to make life easy and to take as many shortcuts as possible while solving. Okay, so those can't be taken unless you know what type of a problem it is. Okay, so we will start looking at exploiting structure within problems. Okay, so all these methods that we will talk are not general. They can't be applied to all convex min LPs. They can be only applied, if you have this type of a constraint or that type of a constraint or these types of variables, not those types of variables. Okay, so these are very, very specific to structures. Okay, but it turns out that when the instances have those particular structures and when you exploit them, you see exponential speed ups. Okay, so something which might be taking 2 hours to solve, and you see that this has this very nice structure, and if you tailor your algorithm for that particular structure, then it can be solved in a matter of seconds. Okay, so huge improvements can be seen. Okay, and Sven talked about traveling salesperson problem. You can give a traveling salesperson problem to a general solver like Cplex or Gurobi by writing the formulation in Ample. But that usually doesn't scale beyond 30 cities, 40 cities, maybe 60 cities. But if you exploit the structure of the constraints and properties of the traveling salesman problem, then you can have a customized solver which can solve problems up to these days up to 100,000 cities. Okay, which is unimaginable given the complexity of number of tools possible. So we will look at some examples of reformulations. I'll start with some very, very simple basic things which we have already seen in this course so far. Okay, just that we didn't call it a reformulation. So the simplest thing that we see is in actually our most favorite method, which is the simplex method, where you start with a problem in the standard form. And as you progress and start pivoting and start jumping from one corner point to the other, you make this transformation to the whole problem, which is some multiplication of this system of equations by a non-singular square matrix. Okay, so if you take B as a basis of any basis of A and you multiply both sides, now your constraints will look very different. Okay, they will have different coefficients, different right hand sides, but the two problems are exactly the same. Okay, they are equivalent. Even though the constraint matrix, right hand sides, and sometimes even the costs, they might be different. So these two formulations are equivalent in the sense that every x which is feasible here is also feasible and it has the same objective value. Okay, so if you find the optimal value of this or you find the optimal value, you are going to get the same solution. Okay, and we don't exploit this fact that that much in the simplex method, but we use it implicitly while trying to solve it. Okay, so one definition of a reformulation could be that given two problems or given two formulations f1 and f2, we can say that f1 is equivalent to f2 if for every x in f1 there is an x in f2 with same objective function value. And also the reverse. Okay, so if and only if not if for every x there is and vice versa. Okay, so there should be if you pick any point in f2, then you should be able to get some point in f1 also. Okay, so this is a very basic definition of equivalence. Sometimes you may relax this definition. This is too strict because sometimes you may add more variables, sometimes you may add more constraints, sometimes you may chop off certain regions which may have suboptimal solutions. For example, you may not be interested in suboptimal solutions. So this is you can take this definition with a pinch of salt, but the general idea should come out. All right. So the idea is that instead of solving whatever is given to you, you solve something else, okay, which might be slightly easier to solve. Okay. Sven gave a nice example of a quadratic problem which can be solved fast. If you remember, he wrote this example. Suppose you have a quadratic of the form x transpose wx plus z transpose x. Okay, and let us say there are no constraints. In one of the applications, he was talking about some inverse problems and such, and suppose suppose w is very big or n is very big. Okay, so n is very large. Okay, so in some applications it may happen that n is the number of variables. X belongs to Rn. Okay, so you have a very large number of variables. That means W is very big, and suppose W is dense, then solving this might be difficult. But if you happen to find a factorization of Z transpose RZ of W, where Z has number of rows much less than n. Okay, so Z is n. So Z is M cross N. Okay. So that means Z transpose is N cross M and so on and so forth. And if M is much less than N, then you can use this substitution and simplify this quadratic significantly. Okay, so huge reductions in solving times. Okay, so these are examples of convex optimization problems, and not Minello's or global optimization. Okay, so so we will see, some of these tricks when we talk about pre-solved methods in the next session, and perspective functions in the session afterwards, and then separability and many other such things in the subsequent days of this course. So so our focus or emphasis is on Minello. So we will look at some specific examples, okay, and try to have a general feeling of what are we trying to achieve by doing these reformulations. Okay, so I will give an example in the context of mixed integer linear optimization, and then we will try to generalize it. Okay, so consider this set S1 is equal to a set of y's binary variables, or let's say x. Okay, so x belongs to 0, 1. Okay, so that means there are k variables, and each of the variables lies between 0 and 1. And we have the following constraint, and there is one binary variable y1 belongs to 0, 1, and suppose I have this type of a constraint x1 plus x2 with these additional upper bound constraints where the right hand side is always y1. Okay, so let's look at the set of all these points. Okay, so suppose these constraints appear in some integer program. Okay, so what this says is that when y1 is 0, then all my x's should also be 0. Okay, and when y1 is 1, the sum of all x's should be less than or equal to 1. Okay, so one of these x's can be 1, not all. Okay. If you look at the LP relaxation, so if I say that, well, what is an LP relaxation? So to get an LP relaxation, only thing I need to change is, instead of y1 being binary, I can do y1 in 0, 1. Okay, so this is my LO relaxation. Okay, so let me just write it here in brief, that R1 is equal to this whole thing except y1 belonging to 0, 1. Okay, rest everything remains the same. Okay, now look at another set S2. Okay, in which I change the first constraint and change the right hand side to y1. Okay, instead of having 1 on the right hand side, I change this to y1, and rest everything is same. Okay. Y1 is still binary. And x is still between 0 1. Okay, so the first question is S1 equal to S2 or not? They are equal, right? If you look at what are the allowed values of x and y, they are same, right? So here also when y is 0, all x's must be 0, and when y is 1, at most one of the x's can be 1. Okay, so clearly S1 is equal to S2. Okay, if I look at the LP relaxation of S2, okay, so what is the continuous relaxation if I ignore the integer restrictions of S2? I will have uh, x1 continuous and x2, oh sorry, y1 also continuous, and rest of the constraints are same as this. Okay, so summation xii less than equal to y1. Okay, what is the relation between R1 and R2? Are they same? They are not same. Okay, so in fact you can show that. What can you show? R2 is a strict subset of R1. Okay, so these two formulations are equivalent as far as integer solutions are concerned, but they are not equivalent as far as their linear relaxations are concerned. Okay, and in fact, if you are doing branch and bound, and if you solve a LP relaxation of this problem, this would be a better approximation. Okay, all right, because it is tighter. The integer points are inside the relaxation. Okay, so the general picture is this. All right, the general picture looks like this. So you have some non-convex feasible region. This could be discrete. This might be continuous. Okay, you can create a relaxation R1. So this is my set S, okay, which I want to solve. So first step is to relax it. Okay, now this might be a poor relaxation as compared to this red relaxation. Okay, which might be a poor relaxation as compared to which is something which is even tighter. Okay, so what is the tightest we can get? What do we call that object? Convex hull. Okay, so ideally we would like to find some reformulation so that we get as close as possible to the convex hull. Okay, so then when we solve the problem, we are very likely to get close to the optimal solution, if not the exact optimal. All right. So all these formulations R1, R2, the systems of constraints which gave us R1, R2, they are equivalent as far as integer solutions are concerned, but some will give a faster solution, others will not. Okay, and if I have many such constraints, okay, these things add up or multiply with each other, and in the end they result in huge differences in time. Okay, so for example, if you have suppose this model, suppose it takes 2 branch and bound nodes, and this takes 4 branch and bound nodes, and if my model has 10 of such constraints and 10 of these constraints, so the difference between them will be then 2 to the power 10 or something. Okay, number of nodes created, because they will multiply with each other. Okay, so these small structures, if wherever you can detect, you should exploit them. All right, so this is one example of structure specific improvements. Okay, so when when you gave a problem to a solver, they try to detect as many such structures as possible. Okay, one other common structure that most of you would be familiar with comes from facility location models, where you can say that S1 is X1 is less than equal to Y1, similar to the previous constraint, versus summation xi I1 to k less than equal to k times y1. Okay, so both the structures say that whenever, sorry, this is y1, all right hand sides are y1. So whenever y1 is 0, everyone should be 0. You can aggregate them into this, okay, but this would be a weaker formulation. Okay. In practice, if k is very large, then it may turn out that if you write it like this, you may get very tight bounds, but the problem itself might get slower because you have too many constraints. So many times, even though you get a tight description of your convex hull or an approximation to convex hull, it is not always true that that largest formulation will actually save you time. Okay, because there are some other trade-offs that you have to worry about. Okay, so but in general, the tendency is that the closer you are to the convex hull of your set of feasible points, the faster you will be able to solve it. Okay, because most of the time in these branch and cut type of approaches is consumed in exploring many nodes of the tree, and that just means that if you have a very big tree, that means you are quite far away from your the linear or the continuous relaxation is far away from the integer points. Okay, that is why you are searching a lot. Okay, so let's look at the so a slightly general view of these things. Okay, so I'm going to draw two non-convex objects, and then write a small result which is somewhat important. Okay, so suppose this is one non-convex set S1. Okay, and we have let's say another one S2. Okay, so S1 intersection S2 is this part. Okay, and if I look at the convex hull of S1 intersection S2, I will get an object which is very close to this. Okay, so that I will draw with this red chalk. Okay, something like this is a convex, smallest convex set that contains it. So this red part is your convex hull of S1 intersection S2. All right. Suppose it is difficult to find this intersection and its convex relaxation. One idea is we can try to find a convex relaxation of S2 separately and a convex relaxation of S1 separately. Okay. So, if I try to do that, then this yellow part is the convex hull of S2, and for S1 I have a similar convex hull. Okay. And if I look at the intersection of these two convex hulls, then I get this region. Okay, which is much bigger than the red region. Okay. So in general, what can I say about this? This is a subset of convex hull of S1 intersection convex hull of S2. Okay. And usually the gap between the two is quite high. Okay. If they are, quite non-convex. All right. And this generalizes to K. So if you have convex hull of S1 intersection S2 intersection S3, so on and so forth, so that would be a subset of intersections of individual things. Okay. So how does that matter? If you have a problem like this, okay, so suppose I say minimize fx subject to g1x less than equal to 0, or let us say xy, with x okay, many times it is very difficult to find the convex hull of the whole set. Okay. So what people try to do, like in the examples earlier, is to just look at few constraints at a time and try to find their convex hull. All right. So in this case you can possibly try to tighten up just this one constraint under these restrictions. Okay. So I might look at the set S1 as just one constraint out of all the constraints that are given, just one or two constraints. Okay. And try to tighten it up as much as possible. Okay, individual constraints as much as possible. So that means, I am trying to tighten this S1 as much. Initial relaxation might be very poor, much poorer than this yellow one, and I will try to get the yellow part. Okay, and similarly I will try to get it for the other set of constraints G2. Okay, and take their intersection. Okay, it would not be ideal. Ideal would have been to look at both of them together. Okay, but that gets hard very fast. Okay, so in all these reformulation tricks, okay, people look for small structures within the problem. Okay, so for example, in facility location model, we just focus on this constraint, summation I going from 1 to k less than equal to ky. Okay, just this constraint where y is binary. okay, and we say that this is a poor way of writing S1. A better, stronger way is to disaggregate these constraints and get a tighter relaxation, okay. So this, this result is uh, quite important. So if you don't know, anything about your problem, how hard or where the difficulties lie, you can start by tightening up individual constraints one at a time. Okay. If that doesn't help too much, then you can start looking at a slightly bigger set. Okay, maybe 2 constraints or 3 constraints together, and try to reformulate them as much as possible. Okay. Uh, and eventually try to build up so that you get the convex hull of the whole problem, which is as hard as solving the problem itself. Okay. So this is the general idea of reformulating things. It is not always true that if you have 2 formulations of a problem, one will always dominate the other. It is possible that none of them dominate each other. Okay. So an example comes out in the famous knapsack problem, and some of you might have seen it. So if I have S1 equal to this knapsack constraint, I hope everyone knows what's a knapsack. Ai yi less than equal to b. Okay, summation. Let us say p. Okay, where yi's are binary. Okay, so this is a binary knapsack where we can select an item or not, and the total should be less than equal to some budget. Okay. So there is a way of rewriting this set as an intersection of all possible covers of this knapsack. Okay. So so let me first write what is a cover. I mean the formulation, then I will just explain. So it just means I belonging to a cover should be less than or equal to mod Cj minus 1. Okay, where J belongs to set of all covers of the knapsack. Okay, so I'll give you an example, and then we will stop. So if my knapsack is of the form 15 y1 plus 10 y2 plus 6 y3 plus 2 y4 less than equal to, let's say, 21, okay, then these 3 first objects, okay, they can't together be 1, okay, because it will violate. Okay, so we say that y1, y2 or first 3 objects create a cover. Okay, a cover is something which will not fit in the knapsack. Okay, so what this constraint says exactly that that out of these 3 items, at most 2 can fit. Okay, no, not 3. All right, and if I write the knapsack, instead of writing it like this, I find out all possible covers. Okay, so what would be a another cover in this case? Y1, Y3 and Y4. Okay, all 3 cannot fit. right? So I will write one more constraint for that, and similarly any more constraints that I can find. So if I write S2 as the intersection of all those covers, it turns out that these two are the same sets, okay, even though this might have many more inequalities, okay, and it turns out that neither is stronger than the other, all right. So it's not that this will give us the convex hull or anything. Sometimes this is actually better, sometimes this is actually better, okay. So it's not that if you have two equivalent formulations, one has to be stronger than the other. It could be that there are some points in the relaxation which are cut off by this, there are other points in the relaxation which are cut off by this, but not this, okay, all right. Even though the feasible points are the same, the integer points are the same, but fractional points may be different in the two sets, okay, all right. So in our subsequent lectures, we will look at many more examples of these automatic reformulations, okay. And if you are solving a particular problem of interest, some robust facility location, or some Steiner tree problem or quadratic assignment problem, then you need to exploit these very structure specific properties. Otherwise, the default implementations will be very slow, okay. So we will look at some of those examples. The pre-solving part is little bit general, and it can be applied or at least tried on all sorts of problems. So they look at some specific things which may be common to many of the models. Then this perspective reformulation and separability, they are applicable for some very specific structures found in several applications, okay. So they are good to have, all right. So many times you might see that structure in 10% of the problems or 20% of the problems, or sometimes 60% of the problems, but not all, okay. But still, if you keep making your bag of tricks bigger and bigger, your hammer becomes more and more sophisticated, and then it can crack more and more problems, okay. So that is the whole idea behind this set of ideas. All right, so with that we can stop.